Swayam Prabha. Digital India. Educated India.
Welcome to the effective stress concept lectures. We are going to cover the concept of effective stress and intergranular stresses between the solid grains. So, in the past lectures, we have covered about origin of soils and their fabric, that is structural arrangement, and interaction with water. With that, we have also attempted to classify the soils, and also we discussed about the compaction characteristics of soils, both coarse grained soils and fine grained soils. Now, we will be discussing about the concept of effective stress, which is very important concept to be understood in geotechnical engineering subject. So, from the previous discussions on the Atterberg limits, classification of soils, soil structure or soil fabric and soil compaction, we must realize the presence of water in soil is very important. So, from the previous discussions from the Atterberg limits point of view, or from the compaction characteristics point of view, or soil particle arrangement or a soil fabric point of view, the role of water is having a great prominence. So, water very strongly affects the engineering behavior of the most soils, especially when it comes to fine grained soils. So, when it comes to fine grained soils, the role of water is having greater relevance. Now, let us define before introducing the concept of effective stress, let us define a water table or a groundwater table, which we refer in geotechnical engineering. The water table, which is defined like this: the natural static water level in the ground at which the water pressure is same as atmospheric pressure is called water table. It is also called as groundwater table or free water surface or phreatic water surface. So, the natural static water level in the ground at which the water pressure is equivalent to the atmospheric pressure is referred as a groundwater table. So, here a cross section is shown, the soil strata, and this is the level at which the groundwater table occurs. So, at this point the water pressure is the same as the atmospheric pressure, which is equivalent to 0, and this is the ground surface which is shown here. So, the groundwater table we have tried to define in this slide is a water table is nothing but a static water surface in the ground at which the water pressure is same as the atmospheric pressure, which is equivalent to 0 in this case. So, this is called a water table and groundwater table or free water surface. This water table levels can fluctuate, it can rise and it can deplete. These facts we will be discussing in the due course of these lectures. So, below the water table, as you have discussed, most of the soils are saturated, that means that all the voids are filled with water, and above the water table they remain saturated depending upon a climatic conditions or particle size and the distance from the water table. So, below the water table, as you have seen, most soils are completely or almost completely saturated. Above water table, the degree of saturation depends upon the climatic conditions, whether arid climates or the climatic conditions and the grain size of the soil and the distance to the water table. So, below the water table most of the soils are basically remain in saturated condition. That means that all the voids within the soil are filled with water, and the degree of saturation depends upon the climatic conditions. One is climatic conditions, other one is the grain size of the soil, and the third one is the distance to the water table. So, the grain size of the soil which is having very great prominence. For example, if you consider here a fine grained soils like clays will remain saturated even above the groundwater table, and for a coarse grained soils like sands and gravels, they remain dry or partially saturated even above the groundwater table. So, this fact is owed to the capillary phenomena, which we will be discussing in the due course of this effective stress concept lectures. So, this slide we have seen earlier also. So, is a cross section of the ground surface is shown here, where the ground is ground surface is shown here, and this is the groundwater table. So, here if you see in this zone above the groundwater table, depending upon the climatic conditions and grain size and distance from the groundwater table, it is possible that this soil can remain saturated or partially saturated. So, if it is partially saturated, it will have some air voids which in between the solid grains, and for some of the voids can also be filled with water. So, water surrounding the particle and points of contact between particles and filling the small void spaces can be seen from this slide. As we have discussed earlier also, we can visualize soil as a grain skeleton. We can visualize soil as a grain skeleton. As it is shown here, this is the individual soil grain, a typical individual soil grain is shown here, and with certain fabric or certain arrangement, and this is the soil skeleton. So, a soil can be visualized as a skeleton of solid particles enclosing continuous voids which contain air or water. So, from the previous discussion, we can say that a soil can be visualized as a skeleton of solid particles enclosing continuous voids which contain water and or air, water and or air. So, the volume of the soil skeleton as a whole can change due to rearrangement of the soil particles into new positions, mainly by rolling and sliding with a corresponding change in the forces acting between the particles. The volume of the soil skeleton as a whole can change due to rearrangement of the soil particles into new positions, mainly by rolling and sliding with a corresponding change in the forces acting between the particles. So, depending upon the stresses which are being experienced by these grains, they can subject it to volume changes either by rolling and sliding which can take place among the grains. So, in this slide what we have seen is that the soil can be visualized as a skeleton of the solid grain particles, particles enclosing continuous voids which are interconnected with water and or air, and the volume of the soil skeleton as a whole can change due to rearrangement of the soil particles. This volume change can occur because of the either a sliding phenomena or a rolling phenomena which is possible between the grains and the application of the stresses. So, in a fully saturated soil, since water is considered to be incompressible, a reduction in volume is possible only if some water can drain out of the soil. That means that in a fully saturated soil, since water is considered to be incompressible, a reduction in the volume is possible only if some of the water can escape from the voids. So, any reduction in the volume is expected only in when water starts draining out of the soil. In a dry or a partially saturated soil, a reduction volume is always possible due to the compression of the air in the voids, provided there is a scope for particle arrangement. So, in a dry or a partially saturated soil, a reduction in volume is always possible due to the compression of the air in the voids, provided there is a scope for the particle arrangement. That means that whether it is in dense state or in loose state, depend upon that particle arrangement will take place. So, in a fully saturated soil, since the water is considered to be incompressible, the rearrangement or a change in volume is only possible when there is a scope for the water draining out of the soil mass. In the case of a partially saturated soil or a unsaturated soil, we can refer which is possible above the groundwater table, that is in the zone of the, that is called Wadhw's zone, where in a dry or a partially saturated soil a reduction in volume is always possible due to the compression of the air in the voids, provided there is a scope for particle rearrangement. So, we have seen here a definition of a groundwater table and the state of the saturation levels below the groundwater table and above the groundwater table. Now, let us try to define what is meant by the stress acting on a certain area due to its own self weight of the soil mass. So, vertical subsurface stress resulting from the soil mass. The stresses in soil mass can be resulted due to its own weight, that is the body forces, and any external loading which is because of any man-made structures or any fuels which are coming up on the soil mass. So, the vertical subsurface stress resulting from the soil mass alone can be computed like this. Suppose if this is the groundwater surface, ground surface, if this is the ground surface, and let us consider this unit weight of the soil is gamma T. The unit weight of the average unit weight of the soil is gamma T, the homogeneous from the ground surface to depth Z. So, let us consider the depth under consideration is Z from the ground surface. So, in order to determine the vertical stress, that is the subsurface stress due to soil mass alone, let us consider a prism which is having a surface area 1 centimeter by 1 meter by 1 meter, a unit cross sectional area perpendicular to the application of the stress. Let us consider a unit cross sectional area 1 meter by 1 meter. So, if you are required to determine the sigma v at a depth Z, so this can be determined like this. This is entirely due to the self weight of the soil which is within the block. So, now if I take cross sectional area is 1 into 1 and the depth of the reference is Z. So, the volume is Z meter cube into the unit weight of the soil mass which has been told as gamma T. So, gamma T into Z is the gamma Z is the stress acting over a unit cross section area at a depth Z. So, we write sigma V is equal to gamma T Z. If T is homogeneous, then if it is a stratified soil, then it is required to be considered depending upon the requirement. So, this particular vertical subsurface stress is also referred as a geostatic vertical stress, a geostatic vertical stress. So, vertical stress due to strata of different soil types. Suppose if you are having a stratification like layers which are deposited of thickness Z1, Z2 and Z3 and having unit weights gamma 1, gamma 2, gamma 3. Suppose if you are required to determine stress at a certain depth Z below the ground surface, then we have to follow this particular procedure. That means that here the unit weights which are referred as the layer A, gamma A and ZA, gamma B and ZB and gamma C and ZC. So, the vertical stress sigma V acting at a depth Z, which is nothing but ZA plus ZB plus ZC is equal to gamma A ZA plus gamma B ZB plus gamma C ZC. So, that is what actually is here has been indicated like sigma V is equal to gamma A ZA plus gamma B ZB and gamma C ZC. So, the vertical stress due to strata of different soil types base can be computed by sigma V is equal to sigma of gamma Z, the summation of the unit weights multiplied by the depths, the layer thicknesses. So, the stresses in soil at any point is the result of the soil above the point or by any other loading imposed onto the soil mass. So, as informed earlier, the stresses in soil mass can be due to its own self weight or due to any other loading imposed onto the soil mass. Suppose the loading can be a concentrated load, a loading can be a line load like a wall which is running over a length L, or a line load representing railway tracks, that can be also referred as a line load, or it can be a uniformly distributed load representing like a fill soil above the certain ground surface. If in that case the stress, which is total stress, can be due to the self weight as well as due to the vertical stress resulting due to the external loading. So, this we will be discussing while discussing the stress distribution in soils due to external loads. So, in this we are considering the geostatic vertical stress, that is merely due to the stress resulting due to the self weight of the soil mass. So, whatever the stress which we are referring is called the total stress, which is due to the resulting load. So, this is indicated by sigma. The total stress is carried by soil solids and water present in the soil mass. So, the total stress is carried by soil solids and water present in the soil mass. So, stress carried by the solids influence the strength and compressibility characteristics of the soils. So, stress carried by the solids can influence the strength and can also influence the compressibility characteristics of the soils. So, total stress has a physical meaning and is making it to be measurable. So, total stress has got a physical meaning in which it is measurable. So, let us consider different cases like homogeneous soil mass. We have already discussed, but let us consider here as a case 1 with a homogeneous soil mass. The total stress at any point is the weight of the soil lying above. That is what we have discussed. Total stress at any point is the weight of the soil lying above the plane at which we are determining the stress. So, sigma v is equal to gamma z. So, this is the element which is sigma v on this horizontal area. The vertical stress acts here at a depth z from the ground surface. So, sigma v is equal to gamma z, and here the unit weight of the soil is assumed as gamma, which is constant for the homogeneous soil mass. This unit weight generally has got a tendency to increase with the depth because of the densification which can result with the overburdens which are lying above the soil mass. So, because of that there is a chance of increase in the density because of the possible densification which can result because of the deposition, that is because of the overburden. The homogeneous soil mass. So, let us consider a small example problem to demonstrate how this can vary and how it can be computed. So, take a simple case. In this problem, gamma is equal to 20 kilonewton per meter cube, which is given as the unit weight of the soil is given as 20 kilonewton per meter cube. Z is equal to 3 meters. So, from the previous deliberations we can say that sigma v at a depth of 3 meters, that is Z is equal to 3 meters, the vertical stress sigma v is equal to 20 into 3, that is 60 kilonewton per meter square. So, let us look into it. Suppose now these are the given parameters, Z is equal to 3 meters and gamma is equal to 20 kilonewton per meter cube. Now, the distribution varies like this. At depth Z is equal to 0, the stress is equal to 0. At depth Z is equal to 3 meters, the gamma Z is equal to 60 kilonewton per meter square, that is gamma Z is equal to 60 kilonewton per meter square. So, this is that variation of the stress is the geostatic vertical stress or geostatic vertical total stress variation with the depth is linear with the depth. That is, here the depth of the soil is like this and the stress is plotted here, then the plot can be obtained like this. So, this is an example problem for a homogeneous soil mass. Let us consider a stress below an impounded water. Soil mass is homogeneous, but a impounded water is acting on the soil mass. So, impounded water acts like surface loading and acts to the geostatic stress at any point in the soil. So, this can result like for example, in lakes or river beds, if a 5 meter water level exists and above the ground surface, then that can act as a total stress at a certain depth below the river bed. So, impounded water acts like surface loading and adds to the geostatic stress at any point of the soil. So, how this can be determined? Sigma V is equal to gamma Z into gamma W ZW. So, sigma V is equal to, now the vertical stress at a particular depth Z below the ground surface is gamma and Z. That is, gamma is the unit weight of the soil and Z is the depth within the soil, and ZW is the weight of the impounded water and gamma W is the unit weight of water. So, the total vertical stress at a point Z below the ground surface is gamma Z plus gamma W ZW. Now, let us look into the example problem relevant to a ground surface with an impounded water. So, example problem states like this: given the gamma is equal to 18 kilonewton per meter cube, the gamma is equal to 18 kilonewton per meter cube, and gamma W is taken as 10 kilonewton per meter cube, approximated as 10 kilonewton per meter cube, and Z is equal to 3 meters and ZW is equal to 1 meter. So, sigma V is equal to gamma Z plus gamma W ZW, that is equivalent to 64 kilonewton per meter square. So, let us look into this problem here. ZW is the height of the impounded water and Z is the depth at which, the reference at which we are trying to determine the vertical stress due to soil mass as well as due to the impounded water depth above the ground surface. Now, if you look into it, these are the depths which are given, 3 meters and 1 meter. In this example problem, we have taken as a 1 meter and unit weight of the soil is 18 kilonewton per meter cube. If the, as we discussed below, because of this it can be, soil mass can be saturated. So, in that case, if the soil mass is completely saturated like river beds, then the gamma has to be considered equivalent to gamma sat, that is the saturated unit weight of the soil mass while determining the total stress at a particular depth. So, if you now consider that deliberation, what we get is a vertical stress due to water which gets added here, and then this is the stress resulting due to soil mass. So, the entire vertical stress at a depth now at a depth of 3 meter below the ground surface is due to the impounded water as well as due to the soil mass stress. So, that is gamma Z is equal to 64 kilonewton per meter square. So, having seen cases homogeneous soil with and without impounded water, let us now consider a total stress in a non-homogeneous soil. So, which is possible when the stratification takes place while forming the soils. When the soil formation takes place, there is a chance of the stratification can occur in the ground surface, below the ground surface. So, the total stress in a non-homogeneous soil, this is a case 3 which we are discussing. A stress at any point in a non-homogeneous soil is due to the individual weights of each layer. That is, individual weights of each layer over a cross sectional area 1 meter by 1 meter which we require to determine. So, sigma V is equal to gamma 1 D1 plus gamma 2 D2 plus gamma 3 into Z minus D1 minus D2. That means that Z is the total depth from the ground surface. So, now the vertical stress resulting due to individual soil weights sigma V at a depth Z can be given like this. Sigma V is equal to gamma 1 D1 plus gamma 2 D2 and gamma 3 into the thickness, that is Z minus D1 minus D2, that is the this thickness which we are referring now. So, let us look into the example total stress in a non-homogeneous soil mass, which is the example for the case 3 which we have introduced in the previous slide. So, we said that in the previous slide sigma v is equal to gamma 1 d1 plus gamma 2 d2 plus gamma 3 into z minus d1 minus d2, that is the depth from the bottom of the second layer surface to the point of the reference at which the stress is being determined. So, let us consider in this example, now these are, let us consider that the layer has layer 1 has got a thickness of 1 meter and has got a unit weight of around 16 kilonewton per meter cube. Layer 2 has got 2 meter thickness and with a unit weight of 17 kilonewton per meter cube, and layer 3 has got a thickness or a depth at which the reference is the stress is being determined is 3 meters and which is having a unit weight of around 18 kilonewton per meter cube. So, in that case we can determine the resulting vertical stress can vary like this, and there is a chance of varying slopes because the unit weight is changing. So, with that there is a change in the variation or a slope of this vertical stress with the depth variation. So, sigma v is equal to, here what we determined from this example is 104 kilonewton per meter square. So, we have seen a homogeneous soil without any impounded water and with impounded water, and a stratified soil as something like a non-homogeneous soil or a stratified soil, and then we try to determine with these examples, 3 examples, a total stress at a particular depth below the ground surface. Now, the case 4 for the determination of the total stress, let us consider a total stress in an unsaturated soil or partially saturated soil. So, soil below the water table remains in a completely saturated condition. That is what we have discussed in the beginning of this lecture. The soil below the water table remains in a completely saturated condition, and above water table soil remains in a complex condition of saturated and unsaturated depending on the capillarity, which will be dealt in the future lectures. So, let us consider a saturated unit weight below the groundwater table. This is the groundwater surface which is indicated here, and this is the zone. It can be saturated, it can be partially saturated depending upon the regions which you have discussed earlier. And case 5, which is the total stress with surface loading. So, this can be like surface loading increases the total stress, that we have discussed. The surface loading can increase the total stress. The load acting on the wide areas are assumed to be constant with depth. Suppose if the load acts over a wide area, something like a wide area fill, or an example with an existing ground level, say if you are reclining the ground. So, that represents a wide area fill over an existing ground surface. In that case, the entire stress transferred directly to the soil mass. It is something like a stratified layer which is coming on above the existing ground surface of a given soil site. So, narrow loads decrease with depth, requiring suitable stress distribution theories to compute the stress intensity at any depth. So, narrow loads like point loads, uniform distributed loads, or strip loading or line loads, they tend to decrease with the depth and require a suitable stress distribution theories to determine their variation with depth or to determine the stresses due to soil mass as well as resulting due to these narrow loads. So, the total stress, if it is there with the surface loading, it has to be determined with soil mass and then the resulting due to the surface loading. Now, having introduced the total stress, now it is required for us to understand and define what is meant by a pore water pressure. We have discussed that the wide spaces which exist in between the solid grains, they are called as voids or pore spaces. If these pore spaces are filled with water, then water exerts pressure in all directions within the solid grains. So, the pore water pressure, which is designated as PWP or also with a letter U, a small u is indicated, and is the pressure in which the water in void spaces or pores which exist between and around the mineral grains. So, pore water pressure is the pressure in the water in the void spaces or pore spaces in which it exists between and around the mineral grains. So, here illustration is shown here. U is the pore water pressure which is designated here, and these are the individual grains which are with certain arrangement, and if you assume that entire pore space is filled with water, so that water is called the pore water or pore water. And this when this is gets under pressure, the pressure which is exerted onto the boundaries of the these grains, in the internal boundaries of this particular pore space is called the pore water pressure, and this can be in any direction because of the Pascal's law principle. So, how to determine this pore water pressure at a certain depth if it is existing in a ground surface or below the groundwater table. So, the pore water pressure under no flow conditions is given by the hydrostatic conditions. So, when there is no groundwater flow either from top to bottom or bottom to top, that is upward flow or downward flow. In these cases there will be variations in the pore water pressure which will be discussed, but assuming that a simple case for the present today's lecture, it can be considered like a static groundwater table conditions. In that case, the pore water pressure under no flow conditions is given by the hydrostatic pressure U is equal to gamma W H. Suppose H is the depth at which actually this pore space exists here. So, this is the pore water pressure, pore water which is filled, pore space which is filled with water, and this depth at reference what we are determining is the H. Suppose we wanted to measure this, we have devices for measuring this pore water pressure at a certain depth below the ground surface. So, here the H is the piezometric head we refer, that is the one which is indicating as a pressure here. So, as the pore water pressure, as the name implies, is the pressure which exists in the water which is present in the pores of the soils. That is what we have discussed in the previous slide, is the pressure which exists in the water which is present in the pores of the soil. The soil pores are normally interconnected. We have seen that the soil pores are something like a skeleton which is having interconnected voids. So, and they may be visualized as being a highly intricate and complex collection of irregular tubes. Suppose if you are having let us consider in this particular slide a soil mass. Let us assume that this is this red line which indicates the groundwater table, and below that all the voids which are filled with water, and when this is under pressure like under no flow conditions, the pressure at the groundwater table surface which is equivalent to the atmospheric pressure is 0. So, below that at a depth z below, what we discussed is that the variation is linear, that is depth is equal to 0 here under no flow conditions, with under hydrostatic when the hydrostatic condition prevails, then at a depth z below the ground surface, groundwater table surface, we can determine the pressure as gamma W z. So, let us consider, suppose if these interconnected voids which are represented as a regular tube with certain diameter, or a certain tube with certain inclination, or a tube with this type of geometry, or a tube with this type of arrangement. If all are interconnected with water, at every level, if this is the water table which is maintained here, it will naturally this water table is maintained, and only here there is a way for escaping water and everything is interconnected. In that case, then what will happen is that each and every point the water pressure is 0, and the water pressure is equivalent to this particular distribution is valid. So, soil having interconnected voids which are similar to irregular tubes, what does it indicate is that the soil is something like having interconnected voids when they are filled, when they are below the groundwater table, at a certain depth the pressure is equal to 0, and below that the pressure increases with the as we go away from the groundwater table surface. So, pore water pressure is the pressure which exists in the water which is present in the soil, in the pores of the soil. So, from this slide what we discussed is that the soil pores are normally interconnected. So, these soil pores we have represented by using some intricate tubes, and we said that even the soils having interconnected voids which are similar to these irregular tubes. So, is something analogous representation we have used here to represent the interconnecting voids within the soil mass. So, pore water pressure, it has a physical meaning, and as I said here, it can be measured. It can be measured by using standpipes or piezometers, or with the modern development, a electronic based strain gauge based transducers are also available to measure the pore water pressure. So, here for pore water pressure measurement, a typical transducers are shown to illustrate the application, how this pore water pressure can be measured in the soil mass. So, in that this is a device which is shown here, which will have a diaphragm fitted with a strain gauge connected in a full bridge to a full bridge in a Wheatstone bridge. So, strain gauge wired to a Wheatstone bridge which is in full form. So, water passes through the porous material and pushes against a metal diaphragm. So, the metal diaphragm is attached to a strain gauge, which actually gives in the form of the tension experienced by the metal diaphragm is reflected as a pressure in the pores in the soil mass. So, the pore water pressure can be measured by using electronic transducers. When the water passes through this porous material, then it exerts pressure on the diaphragm, and the diaphragm will be having a strain gauge arrangement. With that, it exerts a pressure. So, the deflection which is experienced by this diaphragm is registered as a pressure. So, this is how by using electronic transducers one can measure the pore water pressure within the soil mass when the soil mass is completely saturated. When the pore water pressure measurement can also be done with piezometers. So, piezometers are porous tubes that allow passage of water, and the height of water in the tube is measured from a fixed elevation. So, if you insert some piezometers or standpipes, so if they happen to measure the height of the water collected in the this tube with the fixed elevation, that can also be indicated as a pore water pressure or a piezometric head. So, pore water pressure is calculated by multiplying the height, that is the head, with the unit weight of the water. So, boreholes cased to certain depth act like a piezometers. Suppose while doing soil investigations, the boreholes were drilled to assess the soil characteristics as well as occurrence of the stratification and different assess the different properties of soil. So, boreholes which are drilled, boreholes with the casing can also act like piezometers to measure the pore water pressure. Modern piezometers have transducers for electronic recording and data acquisition system. That is also, we have said that the modern piezometers have transducers for recording as well as some automatic data acquisition. So, typical piezometers are shown here. So, with the help of these things one can also measure measure the pore water pressure. Basically, there are two types of piezometers exist. One is a Casagrande's piezometer, other one is the Bishop's piezometer, which are being widely used for assessing the pore water pressure in the field. Now, having introduced the total stress, having introduced the pore water pressure, now we have come to an important milestone in our lectures to introduce about the concept of effective stress or the Tarjagi's effective stress principle, which is very famous particularly in the geotechnical engineering, where it gives about apportioning of the load carried by the mineral grains and pore water pressure. So, Tarjagi 1936 proposed a relationship for the effective stress. All measurable effects of a change of stress such as compression, distortion and a change of shearing resistance are due to changes in effective stress. So, if any effective stress changes occurs, a distortion can occur, or a compression, that is change in the volume, can occur, or a change of shearing resistance can occur if there is a change in the effective stress. So, what Tarjagi has proposed is that an equation which is given like this: sigma dash is equal to sigma minus u. That means, sigma is the total stress, u is the pore water pressure. So, now the new term which is introduced here, sigma dash, which is called the effective stress. Effective stress or intergranular stress, intergranular stress. So, sigma is equal to sigma dash plus u is the famous and first important equation in geotechnical engineering. So, the geotechnical engineering students, whoever learns this soil mechanics or whoever takes this subject, the first and foremost equation in geotechnical engineering is sigma dash is equal to sigma minus u, which is a very important equation, has got many applications in soil mechanics. So, effective stress, if you define, effective stress is the measure of stress existing within the mineral grains. So, which is shown here, the sigma dash which is shown here like a stress which is acting between grain to grain at points of contacts. So, you can see here. So, this is the u which is the pore water pressure existing between the grains, and sigma dash is the stress acting at the grain to grain contacts, mineral grain contacts, and sigma is the total stress acting over entire soil mass. So, the equation which has been proposed by Tarjagi is to relate total stress, effective stress and pore water pressure. So, it causes important changes in the strength, volume and shape. So, effective stress is the one which changes important changes in the strength and volume and shape. Because of this particular stress is named as effective stress. The other name is intergranular stress, but this stress is called effective stress because it is very efficient or very important. It causes important changes in the strength and volume and in the shape which can result because of the changes. So, effective stress is the measure of stress existing within the mineral grain structure. So, how to define this effective stress? So, we have just in the previous slide we have shown that there are three types of stresses. One is the total stress and effective stress which is acting at the grain to grain contact points, and u is the pore water pressure which is exerted within the pore spaces of the soil mass. So, the stress in any point of a section through a mass of soil can be computed from the total stress sigma which acts at this point. If the voids of soil are filled with water under stress u, the total stress consists of two parts. One part acts in the water. So, previous slide we have seen one part is acting in water and the other part is acting in the solid phase in every direction with equal intensity. It is called solid phase. So, one part is acting in the water and other part on the solid phase in every direction with equal intensity. So, this is called a neutral stress. So, here what we have seen is that the water when it is which is experiencing a pressure, it can act in any direction and with equal intensity. So, that is one part of the stress. The other one which is resulting because of the grain to grain contacts, that is the intergranular stress. So, the balance that is of this total stress and pore water pressure is called as effective stress. Sigma dash is equal to sigma minus u, corresponds to an excess over the neutral stress and has a seat exclusively in the solid phase of the soil. So, the sigma dash which is has its seat exclusively in the solid phase of the soil mass. this fraction of the total stress will be called as effective stress. So, what we have discussed is that there are two parts which are if I apportion the total stress, the one is effective stress, the other one is pore water pressure. So, the difference of total stress and pore water pressure, that is effective stress, which is indicated as sigma dash, which is acts exclusively on the mineral grain to grain contact points. So, this fraction of the total stress is called as an effective stress. This fraction of the total stress is called as an effective stress. So, effective stress is not the exact contact stress between the particles. Effective stress is not the exact contact stress between particles, because if you take the grain to grain contacts, particularly in case of granular soils or sandy soils, the grain to grain contact area may be very, very less. So, because of that, the forces, if I take if I take a stress, the stress is the contact stresses at the grain to grain contacts are very, very high. So, effective stress is not exactly the contact stress between the particles, but the distribution of the load carried by the soil or area under consideration. So, stress transfer is through the grain to grain contact points. So, if I take AA is the assumed cross section area, which is passing through the solid grains and as well as through the voids, can be filled with water, with and without water. If you consider like this, AA is the imaginary area passing through the soil mass at a certain depth. BB is the actual cross sectional area, which is wavy pattern. So, while determining this stress at a particular depth, which is BB is approximated as AA, and we determine an average stress acting over at grain to grain levels. So, when we take at grain to grain levels, the actual stresses are very, very high. So, what we discussed in this slide is effective stress is not the exact contact stress between the particles, but the distribution of the load carried by the soil or the area considered. So, stress transfer is through the grain to grain contact points. The stress transfer is due to the grain to grain contact points. So, that is what is shown here in this slide. Two grains with a contact area AC is shown here. So, here if you see, the actual area of stress concentration is less and the stress will be more than the calculated. So, here actual contact area is very, very less. So, with this what will happen is that at this point the stresses are very, very high, but what we generally determine is that acting over an imaginary area passing through the grains as well as through the voids can be filled with and without water. So, let us elaborating about this relationship, sigma is equal to sigma dash plus pore water pressure. Let us consider a piston analogy. Consider a dry condition, assuming that you are having a rigid mold in which the solid grains are filled with and applied with a load is applied, a P load is applied over a cross sectional area A. So, AB is the area which is passing through the voids as well as through the solid grains. And as we have seen, the imaginary area passing through the solid grains and as well as the voids is considered in determining the stress at a particular depth below the at a particular depth within the soil mass. So, load P is applied at the surface of soil through piston and assuming that the valve is closed here, the force P is transferred to the soil grains in the mold through the points of contact. So, stresses at any level AB is equal to P by A, that is resulting due to the stress. So, A is the cross sectional area of the cylinder. Now, let us consider sigma A is the average stress and not the actual stress prevailing at the grain to grain contact points, which is generally very high. That is what we have discussed in the previous slide also. The actual points of contact exhibit a wavy form that is approximated here. The piston analogy, if I look, sigma A is responsible for the deformation of the soil mass. So, it is also termed as effective stress. So, in the case of a dry soil, when there is no water within the voids and it can be referred as UW is equal to 0, then whatever the total stress is applied is the effective stress, which can change the which is responsible for the deformation of the soil mass. So, sigma is equal to sigma dash is the effective stress in the case of a dry soil mass. In case of a saturated condition, let us consider this piston analogy, assuming that the soil skeleton which is there with a certain arrangement filled in a same cylinder filled with water and the valve is closed. Now, the rigid mold which is having a unit cross section area A, which is having a cross section area A, and the pore water which is which indicated with the blue color here, and the valve is closed. The diameter of the valve indicates the permeability or the capacity to allow to drain the water from the soil mass. So, soil is fully saturated and valve is closed, load is applied through a piston. So, in that case load is taken by water in the voids, not the grains. So, if you assume for another analogy for this is that if I replace this skeleton soil skeleton with a spring. So, in that case what will happen is that the soil skeleton is represented by a spring of certain stiffness, and if the same cylinder is filled with water and the valve is closed. So, when the load is applied, the spring will not experience any compression, but the water will be under pressure. Suppose if the water is allowed to drain by opening the valve, slowly the spring experiences compression. So, at any point time t after opening the valve, we can say that the total stress which is applied onto this system is equal to the load taken by the spring plus water. That is nothing but the load taken by the spring, which is analogously is represented here as a effective stress or intergranular stress, is sigma dash plus u. So, with that sigma is equal to sigma dash plus u can be illustrated. So, here the pressure developed in the water is called the pore water pressure. This pore water pressure is also referred as neutral stress. The reasons we will discuss in the next lecture, but now in the saturated condition the soil is fully saturated and valve is closed, load is taken by the water in the voids and not the grains. So, if I look into it, the opening the valve is analogous to the drainage of the soil. So, water flows from some time and ceases, and the drainage increases the intragranular forces. So, once the water escapes from the pore spaces, previously the water which is there in between the soil mass, which is depriving from the grain to grain contacts. So, because of this there is no chance for the grains to come in contact and then mobilize the stresses. Now, having water escaped from the soil mass, they are in a position to apportion the load by mobilizing the grain to grain interaction. So, sigma t, the total stress, is equal to sigma dash plus uw. After complete drainage of water, sigma t is equal to sigma dash. Once the pore water pressure entirely escapes, then since uw is equal to 0, when the pressure is relieved, then after complete drainage of water, then when under no flow conditions, then sigma t is equal to sigma dash. So, we have seen a concept of the effective stress and the first equation in the geotechnical engineering, which is defined as sigma dash minus u is equal to total stress. So, we apportioned, we said that the total stress is applied to the soil mass is apportioned by the grain to grain contact levels, that is at the effective stress and as well as the pore water pressure. So, this slide which shows that intergranular stress or effective stress concept, where we will try to derive or deduce this equation sigma is equal to sigma dash plus uw. So, in this lecture we have tried to introduce the concept of effective stress with a spring analogy or a piston analogy model, and saying that the total stress is equal to effective stress plus uw, and also defined the total stress in case of a homogeneous soil mass with and without impounded water, and a subsoil with different stratifications, as well as with certain with different types of soils, and then their quantifications we have seen, and we also defined the pore water pressure or neutral pressure. So, in the next class we will introduce the effective stress concept, and we will try to deduce these equations with under no flow conditions and with the flow conditions.